So in our last video, we built a reduction half reaction table. We can now use this table to predict whether or not a redox reaction will happen spontaneously. Before we start, it's important to remember that in a solution, molecules and ions act independently. They'll move about independently. When they collide with the right orientation and the right speed, a reaction may or may not occur. It depends on if the reaction is considered spontaneous. Now, to determine if redox reactions are spontaneous or not, we're going to follow the same series of procedures that we did for acid-base reactions. However, instead of using a table of weak acids, we're going to now use a table of half reactions, of reduction half reactions, that can be found on page 7 of your Chem 30 data booklet. So let's start with a specific example. We are going to study a strip of tin being placed in a solution of silver nitrate. Just like acid and bases, we're going to identify all the species in our little beaker or little test tube as either a oxidizing agent or a reducing agent. Now remember, the oxidizing agents are found on the left-hand side of your reduction half table, and your reducing agents are found in the right-hand side of the table. So we have tin, solid tin, silver ions, nitrate ions, and a whole lot of water. We find solid tin on the right-hand side of the table, so it's a reduction agent. We find silver ions on the left-hand side, so it's an oxidizing agent. And we find the presence of water on both the left-hand side and the right-hand side, so water is both an oxidized agent and a reduction agent. So then, after we listed all potential reduction agent and oxidizing agents, we find the strongest oxidizing agent and our strongest reduction agent. Now remember, our strongest oxidizing agent will be on the top left-hand side of our table, and the thing that we find there is our silver ion. So silver ion is going to be our strongest oxidizing agent. And for our strongest reduction agent, or reducing agent, it will be found on the bottom right. And the thing that we find on the bottom right-hand side is our tin solid. Our next step is to write the half reactions for each of the strongest oxidizing agent and the strongest reducing agent. Our silver ion, being our strongest oxidizing agent, gets reduced itself. For every ion, we need one electron to make a neutral silver. Our solid tin, being our strongest reduction agent, is going to give off 2 electrons when it becomes a tin 2 plus ions. So those are our 2 half reactions. Now we're going to balance those 2 reactions by balancing the number of electrons that are transferred. In the reduction reaction, we notice there was 1 electron transferred. However, for our oxidation reaction, we notice there's 2 electrons transferred. The lowest common multiple between 1 and 2 is 2 electrons. So that means we need to multiply everything in our reduction reaction by 2 in order to get 2 electrons. So here we see that we multiply everything by 2, and then when we add everything up together, we have 2 silver ions plus solid tin, yielding 2 silver solid and 1 tin 2 plus ion. And our next step is to determine if this reaction is spontaneous. For our case, our strongest oxidizing agent, silver ion, is above our strongest reduction agent. So indeed, this is going to be a spontaneous reaction. One last thing to check besides the balance of atoms is the balance of charges. Here we know there's 2 plus on the left and there's 2 plus on the right. So the number of ions is balanced as well. In this example, we did not have to balance oxygen or hydrogen using water or hydrogen ions, but it may be necessary in future examples. Let's try a little more sophisticated example. We have tin 2 bromide is poured into acidified solution of sodium dichromate. So tin 2 bromide is aqueous, so it dissociates into tin 2 plus ions, bromide ion. Acidified, it tells us there's a whole lot of hydrogen around, and sodium dichromate, Cr2O7, 2 minus. Looking at our reduction reaction half table, we see that tin 2 plus is both an oxidizing agent and a reduction agent. Bromide, Br minus, is a reduction agent. H plus is could be used as an oxidizing agent. Sodium ion is an oxidizing agent, and dichromate is an oxidizing agent, and water is both an oxidizing and a reduction agent. However, if we look on our oxidizing agent side, the one that's highest on the left is going to be our dichromate along with our hydrogen. And then on the reduction agent side, the lowest reduction agent, the strongest reduction agent, is going to be our tin 2 plus. So now we have identified that the reaction is going to be between a tin 2 plus and dichromate. Now we can figure out our half reactions. Our next step is to write the half reactions. However, we can just look at our reduction half reaction table to write those. Here for the reduction agent for tin, we have to read it backwards, remember, from right to left. We have tin 2 plus yields tin 4 plus and 2 electrons. For our strongest oxidizing agent, dichromate, we have dichromate plus hydrogen plus 6 electrons to yield 2 chromium 3 plus and 7 waters. Next, we have to determine the lowest common multiple between the electrons that are oxidized and reduced. Here for the oxidation reaction, we have 2 electrons, and for our reduction reaction, we have 6 electrons. So therefore, we have to find the lowest common multiple between 2 and 6, and that is 6. That means in this reaction, we need to have 6 electrons that are being oxidized and 6 electrons that are being transferred in our reduction reaction. That really means we need to multiply our oxidation reaction by 3. And then if we do that and we add everything together, we have dichromate plus 14 hydrogen plus 3, remember we multiply everything by 3, tin 2 plus yields 2 chromium 3 plus, 7 water, and 3 tin 4 plus. Check the charges to see if they're still balanced. Here on the left hand side we have minus 2, 14 positives, and 6 positive, for a total of 18 positive on the left hand side. On the right hand side we have 2 times 3 plus, so 6 plus, and 3 times 4 is 12 plus, 12 plus 6 is 18, so yes, our charges are balanced on both sides. Next, we need to determine if the reaction is spontaneous. We find that dichromate is very up high on the strong oxidizing agent side, whereas tin 2 plus is quite low, or is lower than dichromate, and since our oxidizing agent is above our reduction agent, this is a spontaneous reaction. So just a few general hints. Remember, when we deal with any aqueous solutions, we have to remember water. It can act as both a reduction agent or an oxidizing agent. If we're told the solution is acidic, we have H pluses involved. If we're told the solution is basic, we have OH minus that's involved. However, some oxidizing agent and reduction agent have to react together. For example, here, permanganate have to be reacted in an acidic environment. And our last hint is that some species, such as water, iron 2 plus, copper 1 plus, tin 2 plus, and chromium 2 plus can be both reduction agents or oxidizing agents. We have to list them as both. Let's review disproportionation again, because this time we can actually determine if a species can be stable by itself. So if you remember, disproportionation is when a chemical species can both oxidize itself and reduce itself. This type of reaction is called self-oxidation reduction or autoxidation. When you're looking at a table of reduction tables, anything that can disproportionate will be listed as both the strongest reduction agent and the strongest oxidizing agent. So our example here is to determine if a solution of molten chromium 2 chloride be stable. Here the word molten means is this compound chromium 2 chloride is in a liquid form. It's so hot that it's in a liquid form. There's no actual water in the solution here. So we have to list the entities that are both reduction agents and strong oxidizing agents. Here we find that chromium 2 plus is a oxidizing agent as well as a reduction agent. Chloride is a reduction agent. However, chloride is a very weak reduction agent. So our strongest oxidizing agent and our strongest reduction agent is both chromium 2+. Now our following step is to write the balance or write the half reactions. For the reduction reaction, we have chromium 2+ plus 2 electrons to yield solid chromium. For the oxidation reaction, we have chromium 2+ yielding chromium 3+ plus the electron. Our next step is to combine the two half reactions together. However, we have to make sure the number of electrons that is being oxidized is the same as the number of electrons being reduced. So we see here we have in the reduction reaction 2 electrons being transferred. However, in the oxidation reaction we only have 1 electron transferred. Therefore, the lowest common multiple between 1 and 2 is 2. That means in this reaction we need to have 2 electrons that are being transferred over. So therefore, in order to achieve that, we need to multiply the oxidation half reaction by 2 before we combine them in our next slide. So now let's transfer what we wrote on our previous slide. So this is our reduction reaction, this is our oxidation reaction, and notice we've multiplied the oxidation equation by 2 for everything. So now the number of electrons cancels out, so that at the end of the day we have 3 chromium 2+ yielding chromium solid and 2 chromium 3+. The number of atoms on both sides is balanced. We have 3 chromiums on both sides. Charges, let's double check. 3 times 2 positive is positive 6 on the right, and 2 times 3+ is also positive 6 on the right. So the number of charges is balanced as well. The last thing we need to do is predict if this reaction is spontaneous. In this case, we find that chromium 2+ as the oxidizing agent is actually listed below our reduction half reaction table, below our chromium 2+ acting as a reduction agent. So therefore, this is not a spontaneous reaction. It should not react. Therefore, a solution of molten chromium 2 chloride should be stable as is. That is, it will not undergo disproportionation reactions.